Hi everyone, my name is Shubham Mama and today I'll be talking about the traveling salesman problem. The traveling salesman problem, also called the traveling salesperson problem or TSP, asks the following question. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? It is an NP-hard problem in combinatorial optimization, important in theoretical computer science and operations research. TSP as a graph problem. We are given a finite set of points V and a cost CUV of travel between each pair U, V belonging to V. A tour is a circuit that passes exactly once through each point in V. The traveling salesman problem is to find a tour of minimal cost. We can define TSP as an integer linear programming problem. Let's first describe a tour by variables xij, which are binary, that is, they can take the value 0 or 1. Xij will take the value 1 if tour goes from I to j and 0 otherwise. That is, if there is a path exists between I to j, the value will be 1, otherwise 0. The objective function is to minimize the total cost of the tour, which can be written as double summation Cij Xij, where Cij is the cost of taking the path from I to j and Xij represent whether the path is being taken or not. Constraints: enter each city exactly once, which can be written as summation Xij equals 1, and the other constraint: leave each city exactly once, summation Jk equals 1. Next we talk about the problem of subtours. The local constraints that we just defined do not guarantee that we actually find a tour of all n cities. These constraints allow the generation of subtours which are not connected to each other. As we can see on the left hand side, we have some cities, and the middle is an optimal solution of the TSP problem. But the constraints we just defined can also lead to a solution given on the extreme right, where all cities are connected but not completely to each other. Here we see that subtours have formed. How do we eliminate these subtours? In addition to the local constraints, we need some additional constraints which do not allow the generation of subtours in the solution. For every set S of cities, we add a constraint saying that the tour leaves the city at least once. We can represent that mathematically as for every set S, which is a subset of the set 1 to n, the double summation xij is greater than 1. This will happen for any tour. Eventually, we must go from a city in S to a city which is not in S. In the previous solution, the new constraint is violated if we take S to be the set of cities in a subtour. Let's talk about the problem complexity. The local constraints together with the subtour elimination constraints completely describe the traveling salesman problem. The problem is that, let us say if we have n cities, there will be 2 to the power n minus 2 subtour elimination constraints. Thus, with increasing n, the method becomes intractable. There is one thing though which is much easier and faster to do. Given a solution to the problem with just the local constraints, we can quickly find a subtour elimination constraint it violates. We use this idea to get a branch and cut algorithm for solving TSP problems. Let's talk in more detail about the branch and cut algorithm for TSP. We begin by solving the relaxed linear programming problem with just the local constraints. Whenever we get an LP solution that has a lower cost than the best tour found so far, we check the following conditions. If there is some xij which does not belong to the set of integers, we make two branches for xij equals 0 and xij equals 1. If it is an integer solution representing a subtour, we add the subtour elimination constraint it violates. And finally, if it is an integer solution representing a tour, we update our best solution found so far. Now let's talk about some of the heuristics for solving the TSP. Solving the TSP optimally takes too long. Instead, one normally uses approximation algorithms or heuristics. The difference is approximation algorithms give us a guarantee as to how bad solutions we can get, normally specified as C times the optimal value. A common way of measuring the performance of TSP heuristics is to compare its results to the held car lower bound. This lower bound is actually the solution to the linear programming relaxation of the integer programming formulation of the TSP. The solution can be found in polynomial time by using the simplex method and the polynomial constraint separation algorithm. Tour construction heuristics. Nearest neighbor heuristic. In this heuristic, first we select a random city, then we find the nearest unvisited city and go there. Then we check, are there any unvisited cities left? If yes, then we repeat the second step, otherwise we return to the first city. Another tour construction heuristic, nearest insertion. First, we select the shortest edge and make a subtour of it. Then, we select a city not in the subtour having the shortest distance to any one of the cities in the subtour. Then, we find an edge in the subtour such that the cost of inserting the selected city between the edges cities will be minimal. Finally, we repeat step 2 until no more cities remain. Tour improvement heuristics for TSP. First, the two-opt algorithm. This algorithm basically removes two edges from the tour and reconnects the two paths created. This is often referred to as a two-opt move. There is only one way to reconnect the two paths so that we still have a valid tour. We do this only if the new tour will be shorter. We continue removing and reconnecting the tour until no two-opt improvements can be found. Then this tour is said to be two-optimal. Another tour improvement heuristic, the taboo search. A neighborhood search algorithm searches among the neighbors of a candidate to find a better one. When running a neighborhood search on the TSP, neighboring moves are often normal two-opt moves. The problem with neighborhood search algorithms can be they can be stuck in local optimums. The taboo search will allow moves with negative gain, that is, a negative improvement in the solution, if we cannot find a positive one. To avoid revisiting the same moves, the taboo search keeps a taboo list containing illegal moves. After moving to a neighboring solution, the move will be put on the taboo list and will thus never be applied again unless it improves our best tour or the taboo has been proved from our list. Another heuristic for solving TSP, the ant colony optimization. Ant colony optimization is a genetic or evolutionary algorithm which is used in a variety of optimization problems and can also be used to generate a suboptimal solution for the traveling salesman problem. Ants leave a trail of pheromones when they explore new areas. This trail is meant to guide other ants to possible food sources. Let's look how the ant colony optimization algorithm works. We start with a group of ants which are placed in random cities and asked to move to other cities. They are not allowed to revisit a city unless they are completing the tour. This guarantees that there will be no subtours. The ant who picked the shortest tour will leave pheromone content inversely proportional to the cost or length of the path. The pheromone content of each path is updated in two ways. First, evaporation, where the pheromone content in every path decreases with time. And the second, whenever an ant takes that path, thus increasing the pheromone content of that path. The pheromone trail acts as a hint to the other ants taking that path, hence increasing the probability of selection of the path with the highest pheromone content. This process is repeated unless a tour being short enough is found. Conclusion: we defined the traveling salesman problem and how it can be modeled as a graph problem. We formulated TSP as an integer programming problem and defined the objective functions and constraints. We explored the problem of subtours and methods of eliminating them from our solutions. We analyzed the complexity of our solution approach and introduced branch and cut algorithm to solve the TSP problem. We looked at different heuristics for solving TSP involving tour construction, tour improvement, and a genetic algorithm called ant colony optimization. We also described a method for evaluating these heuristic methods using the held bar lower bound.